Okay, so we're into kinetics, which is chapter 20 now. And I started this on Monday, but we did the kinetics lab. The kinetics lab, we're looking at the concentration of crystal violet over time. And so this gets plotted out in the LabQuest system, and you probably notice it's a curve like this. And what that means is that the rate slows down. That is, the rate of reaction here is usually given as the change in the crystal violet concentration over the change in time, delta T. And this is just going to equal the slope, but the slope of this is constantly changing here. And so initially it starts off, let's say, there, but as the reaction progresses, the slope gets slower and slower, that is, less steep as time progresses. And so we have different things I talked about last time. We have things like the instantaneous rate. The instantaneous rate is the slope of the tangent line at a specific time. So if this is the initial time here, this would be the instantaneous rate at times 0. And we call that the initial rate. Okay? Initial rate would be the initial slope. So I don't know if you had a chance to look at Monday's video, but we talked about that. And then sometimes it's hard to draw these tangent lines. And so what we'll do is we'll just get an average rate. And so, for example, if I looked at the average rate over a longer time period, then I'd just pick 2 points and then just average the slope. So it would look something like this. Let's say I want the average rate between this point and this point. So I'll just draw a line. This would be the average rate over this time period from here to here. Now, as the time period gets smaller and smaller, then we will get a more precise measurement of the rate. And if we make that time period quite small, let's say less than 5% reactions occur, then the average rate here and the initial rate here are going to be quite similar. And so we call the slope of the tangent here, this would be the instantaneous rate. And so the initial rate is the instantaneous rate at time 0. And it's going to be approximately equal to the average rate when less than 50% reaction has occurred. So what we want to do is, here would be the average. This would be the average rate when less than 50%, 5% of reaction has occurred. Did I say 50? Less than 5%, sorry. And so if I have less than 5%, I'll just take the average rate here. And it's going to be close to the initial rate. And so I could figure out the rate at any point on this curve or the average rate anywhere on this curve. But what I want to do is I want to represent this as a mathematical equation rather than having to draw the curve and figure it out. And so to represent the rate as a mathematical equation, we have something called the rate law. The rate law tells us that the rate is equal to delta A over delta T, which is going to equal, actually, I need to do a little bit more here, delta CB, in this case, delta T, is going to equal K, which is a constant, times the concentration of CB plus. Law. But there's a problem with this rate, and that is at the same time crystal violet is changing, so is the hydroxide. And so that the crystal violet is going to react with the hydroxide to make crystal violet hydroxide. So both of those are going to impact the rate. That is, as the crystal violet changes, the hydroxide changes, and the rate changes based on that. And so what we do here is we have to do this. For every crystal violet that reacts, I have one. It's a 1-to-1 ratio. And so the rate of consumption of crystal violet is going to equal the rate of consumption for hydroxide. If we're, let's say, a 1-to-2 ratio, let's say I had 1 crystal violet and 2 hydroxides, and the hydroxide has to be consumed twice as fast as the crystal violet. And so it depends on the stoichiometric ratio of consumption there. But we have to throw in this hydroxide in here as well. And we don't know, what's called the order of dependence. We can get the order of dependence from this the graph here. That is, if I cut the crystal violet concentration in half, what does the slope do? Does the slope get cut in half? Does the slope get cut in a quarter, or does nothing happen to the slope? So that's what this M and N tell us. The M and N are the order. And so order. And so this is going to map out this reaction. Now, it's complicated because we have 2 variables. And since we have 2 variables, what we do sometimes is we simplify it into 1 variable. And that's what we do for this particular lab. For this lab, we make the hydroxide concentration very large. If we make the hydroxide concentration very large, it doesn't change much during the course of the reaction. So what we'll say is the hydroxide concentration is fairly constant. We lose maybe a little bit. Fairly constant would be like if you remove a cup of water from a swimming pool, it didn't really change much. And so the amount of water in the swimming pool is fairly constant. So that's it. So if we make the crystal violet kind of low concentration, the hydroxide very high concentration, then the hydroxide is barely going to be consumed during the course of the reaction. And therefore it's fairly constant. And therefore we can simplify this into the rate is just going to equal K times the hydroxide concentration to the N times the crystal violet concentration to the N. And this is going to be fairly constant, and so we'll make this into a new constant called K prime. So this is going to equal K prime times the crystal violet concentration to the N. Now K prime is what we call a rate constant. The rate constant, the bigger the rate constant, the faster the reaction. The rate constant depends on various things. We usually determine empirically, so figure it out. What's going on with that? So in this particular reaction here, what's going on with the slope? What's going on with the slope is this. When we analyze the slope on our crystal violet curve, we see that every time the concentration gets cut in half, the slope gets cut in half. If the slope gets cut in half, then that means M is got to be equal to 1. Because there are different options. There are 3 different options that happen. There are 3 different scenarios that come up. The first scenario is this. This is when m equals 0. When m equals 0, then the rate, it's not necessarily for crystal violet, but we're just going to call it A to the m is equal to Ka to the 0, which is just going to equal K. So the slope doesn't change. We have a constant slope. So it's just a straight line. So as the concentration of A changes, nothing happens to the slope. This is a constant, and this is going to equal delta A over delta T, the slope. That's when m equals 0. When m equals 1, then that's what we call first order. This is called 0 order. This is called first order here. In the first order reaction, if I start off with A here and I cut it in half, let's say I'll end up here, and then I'll cut it in half again, I end up about here. And then I cut it in half again, I end up here. And what we see, it's hard to see from this curve because when we look at a curve like this, it's hard to mentally visualize the slope. But each time I cut in half, the slope gets cut in half. So this slope turns out to be double this slope here. And this slope turns out to be double this slope here. And so on. Yeah. And so each time I cut the concentration in half, the slope gets cut in half. And that means the rate, which is equal to delta A over delta T, is equal to Ka to the first power. And so if A gets cut in half, that's 1/2 to the first power, which means the slope gets cut in half. There's another easier way to recognize this curve. And the easier way to recognize this curve is something called T1/2. T1/2 is the time it takes for half of it to react. And so this, we go from here to here, that's about half. That's going to take T1/2. And then we go from here to here, we cut this in half again. It's going to take the same amount of time, T1/2. This is going to be T1/2. Interestingly, for this one, the T1/2 gets cut in half each time. So here, in the first T1/2 is like this. And the second one will be 1/2 the first T1/2. So it's going to be half T1/2. And then this one will be half the previous T1/2. And so each successive half-life gets half as long. So that's another way to recognize the curve. And, the next scenario we have is if it's second order, like this. If it's second order, then m is equal to 2, and when we look at the concentration, this is the concentration of A, the y-axis, and T on the x-axis. So if we make a plot of the concentration of A versus T, what happens is the slope gets cut by a quarter, because the rate is equal to Ka squared. So if you cut the concentration in half, that's 1/2 squared, which would be 1/4. So this one rapidly slows down. And so if it's rapidly slowing down, then the half-life should be growing. So for example, here, if I look at the first half-life and compare it to the second half-life, the first half-life is going to be half as long. The second half-life is going to be double that. The next half-life is going to be quadruple the initial one, or 2 times the previous half-life. And so the half-life is doubling each successive time. And what we see in the slope is this. The slope is being cut by a quarter. So if we start off with a slope like this, that's the rate. And now the rate is 4 times slower, the slope is. And now the rate is another 4 times slower, and then another 4 times slower, versus half this slope. And so it's hard to see the rate when looking at these tangent lines here. That's what's happening.
Is that With a natural law curve?
No,
No. Oh.
this would be,
Oh.
this one would be the natural law. Just an exponential decay, so.
Got it.
So what we have is let's just come up with the rate law here for a general reaction. The rate is going to equal K A to the M, B to the N, C to the O, dot, 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 however many reactions we have. Now, if we want to do graphical analysis, okay, we need to determine two things in the rate law. We need to determine what M, N, and O, etc. are. We need to determine the order of reaction. And we need to determine the rate constant. What is the rate constant equal to? For graphical analysis, should be A, we need either single variable or pseudo single variable. That is, we only need one concentration change at a time. So single variable is if you just have a simple reaction like A goes to product, so A decomposes in product. That would be this. Or pseudo single variable would be if we had something like A plus B plus dot, dot, dot. What we do is we say rate is equal to K, and then we'll have A to the M, B to the N, C to the O. And what we do is we make two of them very large. So it doesn't matter which two. Let's take the second two here. We'll make B and C very large. If B and C are very large, then it doesn't change during the course of the reaction. If it's very large, like say you spilled some water, a drop of water on the counter here, versus if you lose a drop of water from a swimming pool. If you lose a drop of water from a swimming pool, it doesn't really change. It's very large. But if you lose a drop of water, that is, it evaporates on the counter, then it's significant. And so we make these very large, and then we can make this pseudo single variable. That is, we'll call this K prime, put B and C in there, where K prime is equal to K times B to the N, C to the O. And then this gets the single variable A to N. Okay, likewise, we can make A and C very large. If we make A and C very large, then this is just in a single variable B. Or we make A and B very large, and then we can get C. So we do it one at a time if we have more than one. So for ours, with crystal violet and hydroxide, we'll make hydroxide very large. And then this is only dependent on crystal violet, and then we look at the curve. And then likewise, what we can do is we can make crystal violet very large, so the color doesn't change during the course of the reaction, or it changes very little. And so if you measure the spectrometer, it doesn't really change. What's changing is the hydroxide, and the hydroxide is going to impact the rate, and so we got to see how that impacts the rate. But measuring hydroxide is not so easy because we measure using a pH meter, and pH meters are slow, they're sluggish. They have a glass bulb on the probe, and it takes time to equilibrate. And so you don't get instantaneous readings. We could use a different pH probe. They have semiconductor chips, like a little silicon chip that has a much faster response time. And then you probably can measure the pH. over time and see how the concentration of hydroxide is changing. But by far the easiest is crystal violet there to measure. And so we did the same thing here, we just made hydroxide very large. Once we do that, then we have it in terms of a single variable. And in terms of single variable, what we can do is we can do graphical analysis. But sometimes we don't have to graph anything. Sometimes we just visualize and see what's happening. And so there are different things that we can do. Like, for example, we can make a data table of time versus the concentration. Okay. If the data table has enough data, let's say we start off at time 0 and we had 1.00. And then we look at how long did it take to go half, roughly. How long it takes to go half is, T1 half. We might not have data right there, so we just approximate it. Approximately how long did it take to consume half of it? And then we look, okay, now we're starting at 0.5 to go to 0.25, and we look, how long did that take to go from 0.5 to 0.25? And you have three possible. Do you know what the three possible times are? Because we're limiting this only to 0, first, and second order, as the possible scenarios. We aren't going to, they could be more complicated, but we aren't going to get into more complicated scenarios. So out of those three scenarios, what are the choices? One, for the first half versus the second half, it takes the same amount of time. If it takes the same amount of time, then I know it's what we call first order. If I go from the first half to the second half and it took half as long for the second, then I know it's zero order because each successive one is half as long as the previous one. If I go from the first half to the second half, it takes twice as long, then I know it's second order because each successive half-life takes twice as long. Or we can graph it. If we can graph it, we can see here. And so we can make the graph. Let's say if it's zero order. If it's zero order, then I can make a plot of A versus T. Then each successive half-life takes the same amount of time. And so I end up getting a straight line here. This one looks curved. It's supposed to be a straight line. I can see this first half-life, second half-life, third half-life. Doesn't look quite right, but that would be zero order. If it's first order, then each successive half-life takes half. This is half as long, right? Each successive half-life takes half as long. If it's first order, each successive half-life takes the same amount of time. So this would be first order here. So first order, we would see, okay, the first half would be here, and the second half would take the same amount of time. And the third half would take the same amount of time. The fourth half would take the same amount of time. It'd be something like this. So this would be the logarithmic or exponential type decay here. And so visually we can just see, the zero order would be linear, first order would have this decay. Second order, we would plot it. A versus time, like this. And so it would might start off looking like this, but it would quickly. So the first half-life, but the next half-life would take twice as long. And the next half-life would be twice as long as the previous half-life. So it's going to slow down more rapidly. Okay. Or here's the first half-life. Second half-life would be twice as long. And the next half-life would be up there, 4 times as long. So second order. This is good if you have enough data. If you have enough data, you can map it out. But what if you don't have enough data? What if you only have data right at the beginning? Let's say I have like 5 points right at the beginning. So if I have, let's say, 5 points right at the beginning, am I easily going to see if it's going to kind of look the same, because if I have 5 points all bunched up right at the beginning, it kind of looks linear in all of them, doesn't it? And so it's hard to tell, if I don't have enough data. And the same thing with the data table. I'm not going to have these points. I'm just going to have some points. So maybe the next point's 0.98, 0.94, 0.89. That's not enough data to eyeball and see what the over is. And so if that's the case, then we're going to take some additional steps. It turns out there are 2 equations that we want. The rate law is not that helpful. I mean, it's helpful because it tells us, what's happening with the slope. But it's telling us what's happening with the slope at certain concentrations. Like if I double the concentration, what happens to it? But the other equation that we want is, how long? If we want to make predictions, we'd like to not just predict what the slope is going to be, but we'd also like to predict how long or how much. Let's say, after 60 minutes of reaction, how much is left? Or how long does it take to consume 3/4 of it? Something like that. And so that's going to involve some calculus here. And so what we're going to do is we're going to get the rate law, and we'll get something called the integrated rate law. The integrated rate law tells us how long and how much. The rate law tells us how fast. What is the slope? How fast at a given concentration. The integrated rate law tells us how long, how much. How much was consumed in a certain time period. And so what we do is here, for 0 order, the rate law is the rate is equal to delta concentration over delta T, the slope. And we have different deltas. The triangle delta is usually a big interval. So it could be if I look at delta T could be a big interval, and we can calculate the average slope over that big interval here. But as we make the interval smaller and smaller, then we use different symbols for delta. So for example, a smaller delta might be like this. And so this would be a smaller interval here. And so rather than looking at the slope over this long interval, we might take a shorter interval to look at the slope. Say this interval here, between these 2 data points. It'll be small. But what we can do is we can get a very, very small interval. And that would be what we call infinitesimally small interval, D. And so we use D as the symbol for an infinitesimally small interval. If the interval is extremely small, then it's like a tangent line here. be it. And so this would be something like delta here, and this would be delta, and this would be like d. The interval's so tiny, it's like a tangent right there. This is going to equal k, a to the 0. Well, a to the 0 is just 1, so this is equal to k. And so you do a little bit of calculus. In this case, we don't have to do calculus, but we can. And we get the integrated rate law. The integrated rate law for zero order is a times t is equal to minus kt plus a times 0. This is the usual form of the integrated rate law for zero order. And the integrated rate law for zero order lets us calculate how much is left over at time t after a time interval, or how long. We either solve for a times t or we solve for t. And versus the rate law. The rate law is not that helpful. Well, I guess it is helpful. It tells us the slope here. That's helpful. And so we can get, how did we get m? Well, how did we get m is equal to 0? M is equal to 0. How that was determined was because this. When I cut the concentration in half, nothing happened. If I cut the concentration in half, nothing happens, then it's got to be zero order because there's no dependence on concentration of A. How do I get K? How I get K is just from the slope. So I measure the slope here, and the slope is equal to minus K. And so M can either come from the data table, or it can come from the graph. That is, the slope is not changing. Or it can come from the half-life analysis. There are different ways we can get M here. And K, this is just going to come from the graph. This is the negative of the slope. And then we use the K over here, and then calculate the time. But this also has this form, y is equal to mx plus b. So if we don't have a full curve here, let's say we have a bunch of points and it looks linear, we can't really tell. Maybe the slope will change if we gave it more time. I don't know. Is this going to continue that straight line, or is it going to flatten out? I don't know. And so the other thing we could do is we could do this. We can make a plot here and then test how linear it is, and then compare it to other plots here. So that would be zero order. A times t versus t is going to be linear. Okay, if it's first order, then the rate is equal to delta A over delta T, which will decrease the interval dA over dt, which is going to equal Ka to the first power. That would be the rate law for that. The integrated rate law is going to have two forms. And, well, just 1 minute.
I don't think so, but I left early, so I'm not entirely sure. But nobody else mentioned it, so I'm assuming he didn't. I think he's gonna probably impress on that tomorrow. I know, right? Oh, who knows? I didn't even try the special last exam. It probably was, yeah. If it was simultaneous, I wasn't going to do it. me wrong.
I have a 81, 82 page.
Oh, you're good. You
But
get
then, no, but then, if next exam, I didn't draw, it drops to 70. Because the
Really?
exam, because I remember the first exam, I did a rough, and the second exam, it drops like more than 5%.
Oh, wow.
And then the third exam drops like 3%. So I'm like, if I don't do well in this exam, it drops a lot.
Okay, sorry. All right, so the integrated rate law is going to have two forms. One form is going to be ln of A times t is equal to minus kt plus ln of A times 0. Okay, this form we used to make a graph, so we have y equals mx plus b. And so if we make a plot, the natural log of A versus time, then it's going to be linear. So sometimes it's hard to see, is that curve a first order or a second order? But here, if we do ln of A versus t, it's easier to see if it's linear or not linear. And so when we do our data table for first order, we're going to take our data here and then add one more column, and this would be the ln of A. And then we'll make a plot of ln of A. This would be our y. And this x would be t, the time. So here's our y. And the slope of this is going to equal negative k. So the slope equals negative k. And so m, we can determine m equals 1 because it's first order. That is from the graph visually. And k we can get from the slope of the graph. Negative slope. So sometimes it's a lot easier just to graph ln versus than trying to eyeball it. See if it's first order or not. For second order, and let me do one more equation here. For calculations, how long, how much, we usually use this form of the integrated rate law, which is ln of A times t over A times 0. It doesn't have to be at time 0, just initial, the start time, is equal to minus kt. So how long, how much, we usually use these equations here, and this equation is not easier. For second order, we get that the rate delta A over delta T situation equal to dA over dt, which is equal to Ka squared. And the integrated rate law for this just has one form. We use 1 over A times T is equal to plus Kt plus 1 over A times 0. Okay, so this will tell us how long, how much. You know, if we start at A times 0 and how long it does it take to get to T, A times T, or if I start with 60 minutes of time, how much do I have left? But this also has the form y equals mx plus b. So if we do a plot here, we make a different kind of plot. We would plot 1 over A times t, and then this would be t. Okay, the initial starting point would just be 1 over A times 0 here, although it's going to be down here, so this would be 1 over A times 0. This initial starting point here would just be the ln of A times 0. And then we look at the data. And this should be linear here, but it has a positive slope. It's inverted. So this would be linear. And the slope is equal to k. So our data table, we would look like this. If we plot, this is our y, and this is our x, then it should come out linear. And so using the graphical method, we make 3 plots. One out of the 3 will be linear. The other 2 will be nonlinear. What that means will just be a curve. And so overall, we make 3 plots. So we're going to generate this in our data table. We're going to generate T, concentration of A, which we get from experiment, ln of A, which we get from calculation, and 1 over A, which we get from calculation here. If these 2 are linear, it's 0 order. If these 2 are linear, it would be first order. And if these 2 are linear, then it would be second order. Linear plot. So this is going to tell us the order and the rate constant, K. So let's look at an application of this. Once we have this. Application would be how long, how long. Well, we could do how long does it take to do whatever, 5% reaction, 10%, 50%. And so the application we're going to look at is 50%. How long does it take for 50% or half of it to be consumed? We can call that T1 half. For T1 half, A times T is equal to 1/2 your initial A at the start, which we'll call 0. And so we're going to substitute this in to the 3 half-life equations. So if it's 0 order, then we get A times T, which is going to equal 1/2 A times 0, is equal to minus KT plus A at time 0. So I'm going to subtract 1/2 A times 0 from both sides and add KT to both sides. So I'm going to KT is equal to 1/2 A times 0. And then T1/2, this is T1/2 is how long it takes for half of it, is going to be A times 0 over 2K. A times 0 is a constant, K is a constant. And so this is equal to a constant. Or no, this is not equal to a constant. And A times T, sorry, this is A times 0. Yeah, it depends on your starting. So the starting point changes each successive time. So initially I started at, let's say, 100. And then I dropped to 50. So if I start at 100 and drop to 50, that's the first half-life. Now the second half-life, the initial is going to change because the second half-life is not going to be 100 anymore. The second half-life is going to start at 50. So if I start at 50 here, then it's going to be half as long because it's half the concentration. And so each successive half-life is going to be half as long as the previous one because our starting point isn't the time 0. Our starting point is just where we start. Does that make sense? Okay. So this is it. Okay, that's 0. And then go to first. First. Yeah. So for first, we're going to ln of A at time t over A times 0 is equal to minus kt. So this is the second equation. And so ln at time t is just equal to 1/2 A times 0 divided by A times 0 with initial time is equal to minus kt. And so A0 cancels out and we get ln of 1/2 is equal to minus kt. ln of 1/2 is negative 0.693 equal to minus kt. T 1/2 is equal to 0.693 over k. In this case, k is a constant and 0.693 constant. 0.693 is the 3 sig figs here. You can go more, but this is from the book. And this is equal to constant. And so what this means is for first order, the half-life doesn't change. It's always the same. Okay, let's do second order here. So we have 1 over A times t, which will equal 1 over 1/2 A times start, initial, is equal to plus kt plus 1 over A times 0. So I'm dividing by fraction, so I'm going to invert and multiply. So I'm going to 2 over A times 0 is equal to kt plus 1 over A times 0. So I'm going to go 2 minus 1, which gives me 1. So I get 1 over A times 0 is equal to kt, and t 1/2 is equal to 1 over ka at the starting point. So each new starting point, let's say the first starting point is 100. The next starting point is 50, so that's 1/2. So it's 1 over 1/2. Invert and multiply, that's double. The next starting point is 25. And so each successive starting point is 1/2 the previous one, which means we have to divide by 1/2, which means we invert and multiply, so it's double. Each successive half-life is double the previous half-life. Now, so for first and for second order, the half-life changes, but not first, it's for 0. For 0 and second order, the half-life changes, but for first order, the half-life doesn't change. And so when we think about how fast reactions occur, we usually think about the rate constant. The bigger the rate constant, the faster the reaction occurs. The smaller the rate constant, the slower the reaction occurs. And we think about concentration. The concentration may or may not have an impact. So for example, if it's 0 order, concentration has no impact, it's the rate constant. If it's first order, then both the rate constant and the concentration will have an impact, as well as second order rate constant and concentration will have an impact. Both of those, the higher the concentration, the faster the rate. But the bigger the magnitude of the K, the faster the rate. And so normally we think about how fast a reaction occurs in terms of the rate constant. The bigger the rate constant, the faster the rate. Or we think about how long the reaction takes, in terms of half-life. The shorter the half-life, the faster the reaction. The longer the half-life, the slower the reaction. So, since for first order reactions, the half-life is constant, that's commonly what we use to characterize these. And so, take a look at some first order reactions. In terms of half-life. So this is half-life for first order is given as equation 2014. Half-life for 0 and second order is usually given. Right? The reason is half-life becomes a good way of characterizing how fast reactions occur. And so the shorter the half-life, the faster. And so let's take a look at the half-lives here for some reactions. Here you can see the half-life stays the same. This decomposition of t-butyl oxide. Half-life gives us a visual way of thinking about it as well. So if we look at the radioactive decay of U-238, it takes 4.5 billion years. And so if you have U-238 sample, half of it will decay in 4.5 billion years. In the next 4.5 billion years, half of that will decay, etc. And so radioactive decay is first order. All radioactive decay processes are first order, but there are a lot of chemical reactions that are first order as well in this. So for example, the hydrolysis of sucrose. Hydrolysis of sucrose, which breaks up into glucose and fructose, has a half-life of 8.4 hours. That's 8.4 hours would be a long wait because this is the first step in metabolizing sucrose. And if you're going to metabolize, sucrose is table sugar, but if you're going to metabolize that, you'd have to wait 8.4 hours to digest the first half of it. Well, that's if we don't have any enzymes or acid. In your stomach, it happens very fast. The half-life is extremely short because we have enzymes to speed it up, etc. Here's some. So you can see the half-lives range from very long 10 to the 9th to very short 10 to the minus 7. This reaction happens extremely fast. Now, when we look at the rate constants, a bit more abstract, like 10 to the minus 18. If you have a rate constant of 10 to the minus 18, it's very slow. It's very small, but it's more abstract because it's hard to visualize what's happening. And so for something like U-238, how long would it take for 90% of it to decay? If I have some U-238, how long does it take for 90% of it to decay? I can do it a couple of ways. One, I can use the integrated Wright law. A times t is, I only have 10% left. And so that would be 0.188 times 0, 10% left. And then A times 0 cancels, and I'm taking natural log of 0.1, figure out the time. So I could do that. That's one way. I could just plug it into the integrated rate law and see how long it takes 90%. I would have 10% over. And this is the amount remaining here, the concentration remaining time t. The other way I could do it is I could just visualize it in terms of half-life. So if I start out with 100%, one half-life takes me down to 50%. So that's one half-life. Two half-lives will take me to 25%. So that's 25% remaining, which means 75% reactive. And so for 75% reaction, that would take me 9 billion years to get 75% back. And then I'd go to 12.5% remaining, which means 87.5% reactive. So 87.5% would take me 3 half-lives. Do that. And then 6.25 would be 4 half-lives. That would be, what would that be in terms of percent? That would be 93.75% reaction. And then we go to 3.125. So to get about 95%, let's say go with 95%, it would take at least 5 half-lives. You see that? 5 half-lives. So this is where they come up with the kind of the rough guideline. When people talk about how long would it take for this to decay, normally people, it would take infinitely long, right? Because it would approach 0 at infinity. And so that's not very helpful because all these would take infinitely long. And so rather than that, they say, well, let's just say about 5 half-lives. That 5 half-lives takes you over 95% reaction. And so that would be more useful. So, 5 half-lives of U-238, we'd have more than 95% decomposed, versus 5 half-lives of iodine-131. Iodine-131 only has 8 days. And so 5 times 8 would be like 40 days. And so it'd take about 40 days for iodine-131 to decompose. In fact, they're using iodine-131 as a tell. They had the nuclear meltdown at Fukushima in Japan. And they're worried, is the fission reaction still happening? Is there still a nuclear reaction going on there? Or and if the reaction is going on, then we'll have fresh iodine-131 because iodine-131 is one of the byproducts of that fission reaction. And since it has a fairly short half-life, they can determine that, what's going on. Because if the fission reaction's been thoroughly quenched, or slowed down, they aren't going to be generating fresh iodine-131. But also, iodine-131 too is gets concentrated in your thyroid, and so that's not good to have a radioactive isotope being concentrated in your thyroid. So one of the things that happened during Chernobyl, Ukraine, was that some of the countries there gave iodine supplements or iodide supplements to their population, especially the children, I think. And those countries that gave iodide supplements have much lower cancer rates for the thyroid, much fewer tumors than the ones that didn't. But there they didn't give any iodide supplements for some reason, I think. Anyway, that's just for first order. For second order and zero order, it makes no sense to characterize reactions based on half-life. So for zero and second order, we use K to characterize the rate of the reaction here. Okay, the next way of determining this is this. So I talked about single variable, right? And I talked about keeping the concentration very high. Yeah. The other way of determining the rate law is by doing this. We call B. I don't know if they call the first one A, but method of initial rates. Graphical was the first one. So we don't do the whole graph. We just look at the initial rate. Do you recall what the initial rate was? It would be the tangent at time zero, but determining the tangent at time zero is sometimes a pain. So we just look at the average rate when less than what percentage is reactive. Less than 5%. And so we don't get the whole graph. We'll just get these first 2 points right at the beginning here. And so that's run 1. And then run 2, what we'll do is we'll cut the concentration in half, the initial concentration in half, and then see what happened to the rate. If the rate didn't change, that is, run 2 and run 1 have the same rate, initial rate, then you know it's zero order because we cut the concentration in half, nothing happened to the rate, zero order. The other alternative is if we look at the initial rate, let's say run 1, like this, but when I do run 2, and run 2 I'll start off at half the concentration, and run 2 has half the rate. Then I know it's got to be first order, so I don't have to do the whole curve. Or if I do run 1 like this, and then run 2 is 1/4, then I know it's going to be second order. And so we'll just measure, but normally we don't plot it like this. Normally we'll just put it into a data table and then look at the initial rate rather than the entire thing. So let's take a look at an example of this here. Now, the nice thing about this is we don't have to get this in single variable. We could do this in multivariable as well. Well, we kind of do it in single variable. So if we look at Ka, B, C, M, N, O, etc., then this is what we do. It doesn't have to be very large. So, for example, if we look at experiment 1 and 2, this is not very large, it's 0.105, but the thing is, it's the same concentration. So we have the same concentration initial, so that's not different. And so that means this can change. Whereas when we look at this one doubled, the oxalate concentration doubled. And so what this does is it gets it into a single variable. That is, since this didn't change, this cancels out, and the only thing that's changing is the oxalate. And so if the only thing that's changing is oxalate, what happened to the rate? And so let's take a look at the rate. This is the initial rate, 1, versus initial rate 2. So if we double this, so we doubled the concentration here, if rate 1 doubled, it would be 3.6. But it didn't. It went up to 7.1, which is about quadrupled. And so if we double the oxalate concentration and the weight quadruples, then it's got to be second order in oxalate. That is 2 squared gives us 4, and the rate went up 4 times. So we know then it's second order in oxalate. Write that down. So what we want is we want to get the rate law. The rate law is going to equal K times the mercury 2 chloride concentration to the M times the oxalate concentration to the N. So we held the mercury the same, doubled the oxalate, and we saw that the rate doubled. And so M must be equal to 2. Because if we double this, it's 2 to the N, which is 2 squared, which is 4. All right, let's look at 3 and 2 here. Between 3 and 2, the oxalate stays the same. And what changes is the mercury. And it looks like we doubled it here, going from 3 to 2. So if we double the mercury, what happened to the rate? Well, the rate doubled. We went from 3.5 to 7, going up this way. So if the doubling of the mercury doubles the rate, then it's going to be 2 to the first. And so this is going to be first order. So we can figure that out there just by looking at this. We don't have to do precise calculations for this because we only have 3 scenarios that we're going to be looking at, 0, first, and second. There could be more scenarios, but we aren't going to encounter those. Okay, the next thing we need is K. I don't want to graph it. So we can get K without having to graph it. So we haven't had to graph it really, except just to get these initial rates. The initial rates are just a slope right at the beginning, so we didn't have to graph that either. And it turns out there is, because if I know the concentrations and I know the rate, then the only thing that's missing is, if I know the rate and the concentrations, and I know M and N, then the only thing that's missing is K. So I'll get K from run 1, K from run 2, and K from run 3. So I'll just plug these numbers in and solve for K for each run or trial, and then divide it by 3. They should all come out the same, and I'll get K average. K amperes is what we're going to use for K here. And so now I have the complete rate. But the rate law just tells us how fast, you know. So if I double this, like for example, this tells us how fast. This is what we call third order overall. Third order overall is just a sum. You know, it's first order A, second order B, and it's going to be third order overall. The overall order is just the sum of the individual orders here. And so that means if I double everything, what is going to happen to the rate? Well, if it's third order, it's going to be 2 cubed. So if I double everything, double the mercury, double the oxalate, it's going to go 2 cubed, which is 2 times 2 is 4 times 2 is 8, 8 times faster. And so if I double everything, it's going to go 8 times faster. Or if I cut everything in half, so if I cut this in half, it's 1/2. If I cut this in half, it's 1/4. Altogether, it's going to be 1/8, which is 8 times slower. And so it's third order overall, 1/2 cubed, which is 1/8. And so the rate law is going to tell us how fast, but I want to know how long and how much. But we are not going to do the integrated rate law for more than one variable because that would be too much math for this class. I mean, too many equations to memorize, or if you do calculus, that would be like multivariable calculus. So no integrated rate law. No integrated rate law for multi-variable, that is having more than one concentration change in Chem 1B. If you go into more advanced, then yeah, you'll have an integrated rate law for this. If we have the integrated rate law for this, then we can figure out how long it's going to take or how much we're going to have after a certain period of time. But we're just trying to keep it simple, not too much. There are other ways to determine, you know, the order, and that is time. So, if you think back to your, you know, kinetics, you have run 1 and run 2. And it turns out that the time is going to be inversely proportional to the rate. So the faster the rate, let's say I double the rate, it's going to take half as long. Or, you know, if I double the rate, it's going to be 1/2. If I cut the rate in half, it's going to take twice as long because 1 divided by 1/2 is going to be 2. And so we can get an idea. And so in our lab, we took, in run 1, we took 5 milliliters of sodium hydroxide. In run 2, we took 10 milliliters of sodium hydroxide. So run 2, we had double the hydroxide concentration. What happened to the rate? Did it stay the same? If it stayed the same, then it's 0 order hydroxide. If I doubled the hydroxide and the rate doubled, then it would be first order. If the rate doubled, then it would have taken half as long. So run 2 should have taken half as long to get to the same point, let's say 90% reaction as run 1 did. Or the other scenario is if I doubled the hydroxide and the rate quadrupled. If the rate quadrupled, then it would take 1/4 the amount of time to get. And so about how long did it take? Did it take about, you know, in run 1 going to run 2, did it take about half the time, run 2, or did it take about 1/4 of the time? Or did it take about the same amount of time? Well, we didn't have a mark. We didn't stop. Let's say we didn't stop at 90%. And so it's probably hard to visualize it, but that's another way we could do it. We could just do it based on time instead of rate. The other one is going to be a hybrid method for determining the rate log. What we want to do is, in our experiment, we want to determine the rate law here with crystal violet and hydroxide. Because we know the concentration of hydroxide will have an impact on this. But what we did was we made the hydroxide so concentrated. But even though we made the hydroxide so concentrated, it does depend on the hydroxide, because even what we had in run 1 was we had very large hydroxide, and in run 2 we had very, very large hydroxide. And in both those runs, we would have something like this. So we could say the rate for run 2 is faster, so I'll put it on top, so it's going to have a bigger rate, is going to equal K times the crystal violet concentration in run 2 to the M times the hydroxide concentration in run 2 to the N. And then what I'm going to do is I'm going to divide this by rate 1. So we'll just take a ratio. This is going to equal K times the crystal violet concentration from 1 to the M times the hydroxide concentration from 1 to the N. And then what we did was we made sure that the hydroxide concentration didn't change much. And so we wrapped that into the rate constant. So this is going to be this new rate constant for run 2 here. This is going to equal crystal violet concentration for run 2 to the N, where K prime 2 is equal to K times the hydroxide ion concentration for run 2 to the N. This is going to be divided by K prime 1. K prime 1 is the crystal violet concentration for run 1 to the N. Well, it turns out the crystal violet, we didn't change that. We started off with the same amount of crystal violet in both. And so this is the same. And so this is where K prime 1 is going to equal K times the hydroxide concentration in run 1 to the N. So this is just going to equal K prime 2 over K prime 1. K prime 2 and K prime 1 we get from the graphs. This is from the slope of run 2. This is from the slope of the negative slope. This is the negative slope of run 1. Now it depends on the plot. You know, if it's zero order, it'd be the concentration versus time. If it's first order, it'd be the ln of concentration versus time. If it's second order, it'd be 1 over the concentration versus time. And we get the slope. And so it's going to be plus if it's second order or minus if it's first or zero order. This is going to equal K times the hydroxide ion concentration in run 2 to the M over K times the hydroxide ion concentration in run 1 to the N. Run 2, well, K is the same for both. It's the same reaction. Run 2 is twice the hydroxide of run 1. This is going to be divided by the hydroxide of run 1. And this is all going to be raised to the N power here. And so this is going to equal 2 to the N. So we're going to basically see when we double the hydroxide, we're going to look at the rate constants based on that. Did the rate constant, this is called the pseudo rate constant. Did the pseudo rate constant double? The original rate constant doesn't double. You want to figure out what K is. But did it double? Did it stay the same? Did it quadruple? And so this is going to tell us here what N is, depending on what this ratio is. If it doubled, then N is equal to 1. If it quadrupled, then N is equal to 2. If nothing happened, both of these are the same, then n is equal to 0. So we're going to do this for our data. And then from our data, we're going to calculate what k is. And so this is going to give us n. And then k, we're going to get, k from run 1 is, we're going to get k for the 2 runs. So run 1, k is going to equal k prime 1 divided by the hydroxide concentration of run 1, the n. And for run 2, we get k is equal to k prime 2 over the hydroxide concentration to the n for run 2. These two k should agree. And from that, we'll take k average. And so what we'll get is this. This is going to come from k average over there. N is going to come from the graphs. N is going to come from the ratio of k primes. That is, it's going to be similar to the method of initial rates, but the method of initial rates just measures the rate. Here, we're going to just take the ratio of the k primes to the rate constants, which are going to give an indication of the rate. If k prime 2 is twice k prime 1, then the reaction is twice as fast. If k prime 2 is 4 times, then the reaction is 4 times as fast. Or if it's the same, then it's no change, it's just as fast. And so this is kind of a hybrid method. It's similar to the method of initial rates, but we're using these pseudo rate constants instead. Now, this is all empirical. The rate law that we're getting in these integrated rates, this is entirely empirical analysis. And so it's like the ideal gas law. What we can do is we can use the ideal gas law to make predictions. Well, we can use these rate laws and the integrated rate laws to make predictions of how fast, how long, how much. But what we're going to look at next is theoretical. And so the second half of chapter 20, the first half is empirical. The second half is theoretical. What is the origin of the rate law? And the origin of the rate law is, one of the questions that comes up is, why isn't it this? When I look at the rate law, why isn't it related to A? So why isn't this K, A, to A? Shouldn't these match? And it turns out, no, they might. It may or may not match. Be the same. So we can't say it's the same. That's why we have to pick some new variable, m. And why doesn't it match? I mean, you'd think if you need 1 or if you need 2 or if you need 3, it's going to change how fast it reacts. So let's say I have 3A and 1B, and then 3A, that's got to react 3 times faster than B. Well, that's true, it does, regardless. But is that going to show that kind of dependence here in the rate law? And so the issue comes up is that the reactions are more complicated than they seem. Some reactions are more complicated than they appear. Like, for example, combustion of methane. We out of time? Combustion of methane is very complicated. There's a lot going on. So it's not so simple. All right, so we'll stop here. We're going to analyze our data in the lab tomorrow.